Hey guys, this is Mr. Lewitt, your discrete math instructor for the fall semester of 2021. Today, let's finish up and we're going to quickly go over it. I promise I will try to be quicker than I was yesterday. We're going to go over, wait a minute, what did I do with those problems? Oops, here we go. We're going to go over the last three problems that I suggested for your first programming project. Now remember, you didn't have to do all five. You only had to select one of them, okay? So today, in yesterday's video, I went over this problem and this problem, right? And we went over them in some pretty intense detail, but that's okay. That's definitely okay. And today, let's see if I can be a little bit faster, but no guarantees, no promises. So these are the three problems, okay? So this problem here is from chapter 4, and these two problems are from chapter 5 of your discrete math textbook. So this is something from chapter 4. I believe some of this stuff should have been in your chapter 4 homework. I know for a lot of students, a problem like this seems confusing, but let's talk about it. It is an interesting problem, okay? So what this problem says is find all solutions, if any, to the system of congruences x is congruent to 5 mod 6, x is congruent to 3 mod 10, and x is congruent to 8 mod 15. So that seems a little abstract and weird. So let me rewrite those equations in a form that might be easier for you to understand, okay? So this first equation here, what it really says is x minus 5, okay, x minus 5 mod 6 is equal to 0. That's really what it says, okay? And then the next equation says, x minus 3, okay, x minus 3 mod 10 is equal to 0. And then, of course, this equation, it follows the same pattern as the other two. It's going to be, x minus 8 mod, okay, 1 second, mod 15 is, whoops, 1 second, is equal to 0. Okay? So we have to figure out solutions to those three equations. It's really a system of equations, okay? But it's solved a little bit differently from the linear equations that you remember from college algebra. In college algebra, you had these equations, x plus y, is equal to 1, let's say 2, and x minus y, is equal to 0, and you could solve this using substitution, addition, determinants, matrices, matrix inverses. So here what we have is a little bit different. It's a little bit different, okay? But in some ways it's similar. Okay, so I'm going to solve this one using Racket. Okay, so this problem in yesterday's video, I solved this problem with Python, and then I solved this problem with Mathematica. And so this problem I'm going to solve with Racket. I know some of you think Racket is complicated, and it is, but actually, please, is there such a thing as a simple programming language? A lot of you guys think that Python is simple, but that's only because you've been using it for a long time, and that's why you think it's simple, okay? But I bet the first time you opened up a Python shell, you probably thought, oh wow, this is hard, this is complicated. So everything, if you don't know a lot about something, it's going to seem very complicated. But as you learn more and more and more about it, it seems less complicated. And that's true of everything, including programming languages, okay? So let's try this problem using Racket, all right? Let's see. Okay, hold on one second. So, well, you know what I'm going to do? Hold on. Let me quit. Okay. There we go. I'm going to open up a new Racket shell. Your logo is probably different from mine. Yours is probably red, white, and blue. Mine is yellow and orange. Not sure how that happened, but that's okay. Okay, so I'm going to try to do this as quickly as possible, but if I do it too quickly, you're just going to get very confused. So that's not good. Okay, so the first thing I need to do is turn these congruences into functions. I need to turn these congruences into functions, okay? So let's see. Define equation 1x. Now when you're comparing numbers, guys, you can just use the equal sign in Racket. If you're comparing other types of data types, other types of objects, you should really use equal question mark. But for just regular numbers, it's sufficient to use the equal sign. Okay, modulo. Let's see, x minus 5, x minus 5, and let's see, that, excuse me, that's going to be a 6. Okay. And that's going to be equal to 0, or I could put the 0 here. It really doesn't matter. Okay. And of course, what I should do over here, I should type, Douglas E. Lewitt in Math 144, section 0C1. Solving a system of three congruences from chapter 4. Okay? And so that is my first equation. Equation 2x. Oops. Modulo, okay, what are the numbers that we have? 3 and 10, x minus 3 mod 10. So x minus 3 mod 10 is equal to 0. And then, excuse me, x minus 8 mod 15 is right over here. So we're going to define our function. Okay. Modulo x, what was that again? Hold on one second. That was x minus 8 mod 15. X minus 8 mod 15. Okay. Our definitions work. Now we're going to need the GCD and LCM functions. We need the GCD and the LCM functions. All right, so this stands for least common multiple, and this stands for greatest common divisor. So we need those functions in order to figure out an upper bound. And you'll see what I mean in just a moment, okay? So let's see. Define greatest common divisor of two numbers if x is equal to 0, give me y. Otherwise, GCD modulo yx and then x. That's the classic recursive definition of greatest common divisor. This is actually, this is called the Euclidean algorithm for finding the greatest common divisor of two numbers. Okay, actually, I should write that. I should really write that over here. Okay. Put a little space there. Okay. And the LCM, define the LCM of two numbers. That is simply going to be the quotient. That's going to be the quotient of the product of x and y divided by the GCD of x and y. So that's a pretty simple algorithm. Now let's see if all this works. Okay. GCD of 3 and 9 should be 9. I'm sorry, should be 3. That should be 3. And the LCM of 3 and 9, that should be 9. The GCD of 15 and 30, 35. I believe that's 5. And let's try at the other, let's try to reverse the arguments and see what I get. Should be the same. And what about the LCM of 35 and 15? It should be 105. So let's see, 35 times 4 is, no, 35 times 3 is 105. And then, let's see, that would be 15. Let's see, 15 times 7. 15 times 7 is 105. So 105 is the least common multiple. That's the least common multiple of 35 and 15. And the greatest common divisor of 35 and 15 is 5. So it looks good. So here's what we need to do. We need to figure out, here, let's refresh this. We need to figure out the LCM of these three numbers. So we have 6, 10, and 15. So 6, 10, and 15. And that's going to be 30. Okay. Whew. Excuse me. Okay. Didn't get quite enough sleep last night. So, if there is an answer to this problem, if there is an answer, it's going to be somewhere in the range. It's going to be somewhere in the range between 0 and 30. If there is an answer, it's going to be somewhere in the range between 0 and 30. So how do we figure that out? Well, we can define a function. Find solution, start and finish. Okay, if start, and start is probably, let's make it 0 and finish will be 30. If start is greater than finish, return false, which just means no solution. There is no solution. Otherwise, okay, if and equation 1 starts, equation 2 starts, equation, oops. There we go. Equation 3 starts. If all of these are true, then simply return start. Otherwise, follow the recursive path and increase start by 1. Find solution, 1 plus start, and then finish. Okay, so let's see if that's going to work. Find solution 0, 30. Okay, so 23 is one possible solution. 23 is one possible solution. Equation 123 should be true. Equation 223 should be true. Equation 323 should be true. All right, but what is 23 plus 30? That's going to be 53. So equation 1 of 53 should also be true. Equation 2 of 53 should also be true. Equation 3 of 53 should also be true. And actually, the solution is going to have this form. The solution is going to have the form 23 plus 30 multiplied by n, where n is simply an integer. It could be a negative integer, it could be a positive integer, it could be 0. Okay, so, you know, let's try it. So 23, 30 times negative 4. Okay, negative 97. Excuse me. Equation 1, negative 97 should be true. Equation 2, negative 97 should be true. Equation 3, negative 97. Again, it's true. Very simple. It's really not hard, guys. All right, so I can certainly email this to you, and you can take a look at it. All right, so yes, we can save. The save file operation failed to connect to the open and save panel service. Okay, that's weird. Why is that going on? Okay, hold on a second. Save definitions as. That is really, really weird. That should not be happening. Okay, so there's a problem with my racket installation here. I cannot seem to save. Wait a minute. That is really, really weird. Okay. That is not good. Yeah, there's something wrong with this racket installation. I'm using a different computer from the one I used yesterday, and this is really not good. The save file operation failed. The save file operation failed to connect to the open and save panel service, which is really bad. So the only thing I could think of, let me see. Let me see if I can copy. Yeah, that's really weird. Okay, I'm having some minor issues with my racket installation on this particular computer. It's not the same computer that I used yesterday. So this is not too good. So let me see here. I'm going to copy that and okay. Let me see. Okay, let me see. Let me see if I can do it this way. No guarantees. Let's see. Programming project number 3.rkt. Hey. All right, 1 second. All right, why is this taking so long? Okay, there we go. All right, let me see if I can paste this. All right, let me see if this is going to work. Oh, come on. Come on, come on. Oh, no wonder this is because I quit. Okay, let me see. Oh, come on. Save file, yes. Okay, so yeah, that really should not be happening. That's totally messed up. Okay. 1 second. Let's see if I close this. Yeah, that's ridiculous. Okay, don't save. All right. So, um, okay, programming project. Where's the programming project? Here we go. It's right over here. Hopefully we can open it. Okay, so that was kind of a roundabout way of doing that. That was weird. That was a little weird. I'm going to have to check my Racket installation. That should not be happening. So, okay. Let's run this. And again, let's try this. Find solution 0 LCM. And what are the three numbers again? 6, 10, and 15. 6, 10, and 15. Okay, so it works. I had to save it using a different text editor, which is really weird. I'm going to have to check my Racket installation because something is not quite right. That's very, very strange. Okay, but basically that's it. I will email this to you guys, and that's it, okay? So for the last two problems, guys, I'm going to use Python, and I'm going to kind of go through this a little fast so that the video isn't going to become ridiculously long, all right? So I will definitely have to check my Racket installation. That's definitely kind of weird. Screen Recorder Pro, Screen Capture HD video. Okay, let me just pause the video for a moment, guys. Okay, guys, actually, I paused the video for a few minutes and I did look it up, and apparently, I'm using the latest version of Mac OS. I'm using Mac OS X Monterey. So, if you apparently Racket is behaving a little strangely on this new version of the Mac operating system. So Dr. Racket cannot save files on Mac OS Monterey. If you go over here, yeah, you can actually see, there's a whole question and answer thing going on here. You can let me see. I think yeah, this site might be a little bit better. I actually tried doing. Let me see. Yeah, this was the error that I was getting. This was the the save file operation failed. The save file operation, excuse me, the save file operation failed to connect to the open and save panel service. Um, and apparently there is a good fix. And basically just open up Dr. Racket, require the framework, preferences colon set, um, you know, apostrophe framework colon file dash dialogues apostrophe common. And that does work. Close this file, and then after opening up Dr. Racket, you will be able to save your work, although you won't get a very attractive dialog box. The dialog box is a little more primitive, but at least it does work until, I guess, hopefully, they will fix the issue when they come out with Racket version 8.3 or 8.4. But yeah, so I actually this morning I did install the latest version of Mac OS, and unfortunately, yeah, unfortunately, so Dr. Racket does seem to have some issues on this version of Mac OS. It basically works, but saving files can be a little challenging. Okay, so but this appears to basically do the trick. It basically does the trick. Okay, at least for now, it's a workaround. It's a hack. It's what you would call a hack. Okay, so let's quickly go through the last two problems, guys, and we're just going to call it a day. All right. So let's see. So given a list of integers and an element x, locate x in this list using a recursive implementation of linear search. Now, for this particular problem, the list does not have to be sorted. For this particular problem, if you're doing a linear search, it doesn't matter if the list is sorted or if it's not sorted. If the list is sorted, that's great. If the list is not sorted, that's great too. It really doesn't make a difference. It only matters when you're doing a binary search. For number 10, given a list of integers and an element x, locate x in this list using a recursive implementation of a binary search. It seems to me like most of you guys picked one of these two problems. Most of the students in the class picked either number 9 or number 10, and that's perfectly okay. But you should still be aware of how to solve these other problems. Before you finish this course on December 15th, I think it would be great if you knew how to figure out number 7, number 8, number 26. You should be aware of how to solve those problems, okay? So very quickly, I'm going to go through this kind of fast, guys, because I don't want this video to get super long. Okay. If you're doing a linear search is very easy. So, and in fact, guys, I'm not even going to bother saving these functions to a file and emailing them to you because I think most of you are very comfortable with these two problems. And in fact, most of the students in the class actually did either problem 9 or problem 10. You either did a linear search of a list or you did a binary search of a list. So I'm going to go through these problems quickly. I'm not going to save these functions to a file and email you the file because I think most of you know how to do 9 and 10. So we're going to do this pretty fast. So we're going to do define, I'm using Python here, linear search. This is some element x, and I have a list of x's, okay? And okay, so remember in Python, any collection, excuse me, any collection in Python, a dictionary, an array, a set, a list, you can transform it into a Boolean value. You can cast it to a bool. If it's empty, then when you cast it to a bool, it's going to be false. What is not false? Not false is true. So here we could simply say return, or actually we could do a print. We could do a print statement, print element X not found in list. Okay? Else we could do, okay, head X is 0, which gives me the first element of the list. Oh, wait, one second. Sorry about that. And then we can do tail, give me everything except the first element of the list. Okay, so let's see. If head is equal to X, then we can print element X is contained in the list. Okay. Else, linear search X tail. And we do have to return that. We do have to return that. Okay. All right, let's see if this works. Linear search 3, 1, 2. Element 3 not found in list. Linear search 3, 1, 2, 9, 10, 3. Element 3 is contained in the list. Very simple, right? I mean, it's really not a big deal. It's pretty simple, right? Okay. So, I mean, and this list doesn't have to be sorted. When you're doing the linear search, it doesn't make a difference if the list is sorted or not sorted. Now, binary search is a little more complicated, but it's really not that big a deal. So basically, the first condition is your list has to be sorted from smallest to greatest. Actually, it really could be sorted from greatest to smallest, and you would get the same answer, but your code would look slightly differently, but that's not a big deal. So for this one, you have to be careful. If I have a list, my list is equal to, let's say, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Okay. So how do I get the middle? Actually, you know what? Let me use a different example. My list is equal to Zeus, Hera, Ares, Athena, Artemis, Apollo, and Hephaestus. Okay. And Aphrodite. These are Greek gods. Aphrodite, and we have, oh, let's see, who else? Hestia, and we have Poseidon and Hades and Hecate, and we have many others. Okay, so that's enough for now. Okay, so this is my list. So how long is my list? I have 12. Oh, I forgot Mercury. Okay. I should put Mercury in there. He's important too, right? Or Hermes. So my list is equal to Hermes, okay, plus my list. And now my list starts with Hermes, and the length of my list is now 13. Okay. So how do I get the value in the middle? So middle index is equal to the length of my list, integer division by 2, and then I would say my list middle index, and that's going to be Apollo. So what if I want the list, everything in the list up to the middle index? It's going to be my list, middle index. And that's going to give me, let's see, Hermes, Zeus, Hera, Ares, Athena, Artemis, and Apollo's in the middle right over here. Now, what if I want everything to the right of Apollo? My list, okay, it's going to be 1 plus middle index, right? And that's going to give me everything to the right of Apollo. So it's going to give me Hephaestus, Aphrodite, Hestia, Poseidon, Hades, and Hecate. Okay. So when you're doing the binary search, guys, you're going to basically use the same idea. You have to partition your list into basically 3 parts. There's the value in the middle, there's the stuff to the left, and then there's the stuff to the right. Okay, so define binary search. We have an element X and a list X's. Okay, so if our list is empty, we could say print element X, that's an F string literal, if, okay, element X is not contained in my list. Okay, right? Otherwise, so if, okay, so if the element X, so if the list is empty, if the list, this means if the test to see if the list is empty. So if the list is empty, print element X is not contained in my list. Otherwise, okay, we're going to do middle index is equal to the length of X's, integer division by 2. The first half of the list is going to be X's, everything up to the middle index, which is, let's see, that's what we have right over here. And then the second half is going to be X's, 1 plus middle index. Well, let me see here. I think that should be okay. Actually, I put a space. I'm not sure if that space is really necessary. I'll put it in there anyway. I'm not sure if that's really necessary. I don't think so, but it might be. Okay, and then middle value is equal to X's middle index. And now we have another if-else statement. So we have if, okay, so we're going to have if, wait a second. So if X is equal to the middle value, then we're going to print element X is contained in my list. Otherwise, elif, if X is less than the middle value, then we're going to return, let me see, then we're going to return binary search X first half, else if it's not equal to and it's not less than, then it must be greater than, and then we're going to return binary search X second half. Okay, so this function, it only works if your list is sorted, and the reason is because of what's happening over here. You're doing, less than, greater than, equal to, so that's really a big deal, okay? So binary search 1, 2, 3, 4. Element 1 is not contained in my list. Binary search 1, 2, 3, 4, 5. Element 1 is contained in my list. Binary search 1, 1, 2, 3, 4. Element 1 is contained in my list. Binary search. Well, actually, with strings, it's going to be a little bit different. So, okay, so -3, 5, 6, 7, 8, 9, 10. Element -3 is not contained in my list. So what happens if the list is not sorted? That could be a problem. So let me see. That's interesting. So it did, hold on one second. It still worked, although the list is not sorted. Yeah, let me see if this works. Yeah, see, this does not work. So here, this is interesting. It worked because the 1 was on, well, you have a greater number, you have 0, which is less than 1. So this half of the list is actually sorted. This half of the list, if you just look at 0, 0, 1, that's going to be sorted. But here you have 1, 5, 9, 0, 0, 0. The only part of the list that's sorted is the 5 and the 9, but everything else is not sorted. And as you can see, the binary search failed because the list is not sorted. So, it says here, element 1 is not contained in my list, but you and I both know element 1 is contained in the list. So for binary search, it's important that your list has to be sorted. Your list does have to be sorted, okay? All right, guys, I think that's enough. I'm just going to email you the Racket file. I'm not going to email you the Python code because I think most of you are pretty comfortable with the recursive linear search and the recursive binary search, okay? So I'm just going to email you the recursive, my recursive solution in Racket for figuring out the system of congruences. And for the binary search, you can just look at my video, and that really, for the linear search and the binary search, just look at my video, and I think that's going to be enough, okay? All right, guys, take care, and happy Halloween. Take care, okay? Bye-bye.